In this video, we look at calculating TOLD for the T-6. Takeoff and landing data is typically provided to you for home station sorties, but it's important to know where these numbers came from. Off station, such as during cross-country flights, you'll have to calculate your own TOLD. In this lesson, we'll look at a handful of the most common charts you'll need to be familiar with in the T-6. The publications used for this presentation are the T-6-1, Appendix A, and the abbreviated checklist, Performance Data section. In the example TOLD calculations, we'll be taking off from Albuquerque, New Mexico. The assumptions used are taking off from runway 8, which is 13,800 feet long. The runway is dry and has a slope, or runway gradient, of 0.5% up. The calculations will be based on using 0 knots of headwind, outside air temperature of 27 degrees Celsius, and a takeoff weight of 6,500 pounds. In several of the TOLD charts, we'll need to know the pressure altitude. Pressure altitude is important as a basis for determining engine performance. Pressure altitude is the height above a standard datum plane, which is a theoretical level where the weight of the atmosphere is 29.92 inches of mercury. Air is denser at sea level than aloft. As altitude increases, atmospheric pressure decreases. This difference in pressure at various levels causes the altimeter to indicate changes in altitude. When the aircraft altimeter is set to 29.92, the altitude indicated is the pressure altitude. Here, the altimeter reads approximately 5,040 feet pressure altitude. In the METAR, the barometric setting is 30.21. With an altimeter setting of 3021, the altimeter reads field elevation. Pressure altitude can be calculated using the METAR altimeter setting. Every 1/100th of an inch of mercury equals 10 feet. If the altimeter setting is higher than 29.92, the pressure altitude is lower than field elevation. 30.21 inches of mercury is 0.29 inches above standard. This equates to 290 feet. Subtracting 290 feet from field elevation gives us a calculated pressure altitude of 5,065 feet. In the TOLD charts, we'll round this to 5,000 feet. Standard sea level free air temperature is 15 degrees Celsius. Given a standard temperature lapse rate of 2 degrees Celsius per 1,000 feet of altitude change, the standard temperature at 5,000 feet is 5 degrees Celsius. That puts Albuquerque at 22 degrees above standard temperature, which means density altitude is higher than pressure altitude. Use of an E6B shows that the density altitude at Albuquerque is 7,647 feet. Pilots must understand how the performance of the aircraft is directly related to the density of the air. Air density affects how much power a naturally aspirated engine produces, as well as how efficient the airfoils are. If there are fewer air molecules to accelerate through the propeller, the acceleration to rotation speed is longer and thus produces a longer takeoff roll, which translates to a decrease in performance. In the T-6, torque output at 60 knots indicated is the primary indicator to the pilot if the engine is producing predicted performance. For abort decisions, enter the min power at 60 knots chart on page P7 of the abbreviated checklist with IOAT to determine this torque value. In this example, min torque at 60 knots indicated is 98%. If this torque value is not achieved by 60 knots indicated, the takeoff should be aborted. We'll now calculate our takeoff distance. This chart can be used to find your ground run or the total distance to climb up to 50 feet AGL, sometimes referred to as a screen height. Starting top left at 27 degrees Celsius, trace straight right to 5,000 foot pressure altitude, then drop down to the baseline of the takeoff weight grid. Since the gross weight is 6,500 pounds, trace straight down to the baseline of runway gradient. The runway gradient is 0.5% up for runway 8, so at the baseline trace up to 0.5, then straight down to the baseline of the wind component grid. This amount of gradient on a nearly 14,000 foot runway is negligible in the T-6, so for other charts in this lesson, we'll use 0% runway gradient. The winds are pretty calm, so we'll trace straight down to the obstacle height baseline. But as you can see in this chart, a headwind decreases takeoff distance and a tailwind increases it. With a headwind, if you rotate at 85 knots indicated, the aircraft will be less than 85 knots ground speed. For conservative numbers, any headwind could be disregarded running charts since that results in better than expected performance. Always account for tailwinds though, and avoid them whenever possible, especially on shorter runways or if departure obstacles are a factor. In our example problem, 2,400 feet is the flap's takeoff ground distance to accelerate to 88 knots indicated. Next we'll calculate VB, max braking speed. As you likely already know, VB is the speed at which brake failure is expected. This chart is somewhat confusing to use, but if used correctly, it provides the brake application speed at which 3.96 million foot-pounds is reached, as well as the expected energy absorption at actual brake application speed. Starting at the top left, 27 degrees Celsius, trace right to 5,000 foot pressure altitude, then straight down through 6,500 pounds takeoff weight to the brake application baseline. Here we will hold momentarily. Now we need a second line starting from bottom left, 0 knots wind component, trace that right to 3.96 million foot-pounds, and then straight up to the brake application baseline. That blue line continues upward until it is at the same point on the curve as the first line traced in red. Now a line is drawn on the brake application grid that connects these two lines. This green line will be used to find VB and energy absorption amounts at airspeeds below VB. To find VB, go to the point where the blue line intersects the green line and then trace straight left. This is VB, which is 102 knots indicated in this example. If brakes were applied at 85 knots indicated, the brake energy absorption is approximately 2.9 million foot-pounds. We'll now look at max abort speed. There are two primary factors that affect abort speed: runway length and brake energy absorption capability. If you abort a takeoff above a certain airspeed, you'll either run out of runway, smoke the brakes, or both. To figure out your max abort speed, you first have to know your max braking speed. As you'll recall, VB was calculated at 102 knots indicated. We'll now run the max abort speed charts starting top left at 27 degrees Celsius. Go right till 5,000 foot pressure altitude, then go straight down through 6,500 pounds until reaching the runway available baseline. Follow the curve to where it ends at 10,000 feet. The line then goes straight down using 0% runway gradient, 0 knots of headwind, and a dry RCR. You'll notice from this chart abort speed is affected most by runway surface condition and length. A long, dry runway yields the highest abort speed, in this case 114 knots indicated. If brake failure were not a consideration, the aircraft could accelerate to 114 knots and still stop on a 10,000 foot runway. Considering this runway is nearly 14,000 feet, plus has an additional 1,000 feet of overrun, the actual charted abort speed is well over 114. There are two issues with this abort speed though. The first is at 114 knots, the airplane is generating plenty of lift for flight, and it is well above landing touchdown speed. Second, brake failure would occur above 102 max braking speed. Despite the long dry runway, the max abort speed in this scenario is 82 knots due to braking limitations. Above 82 knots, you should consider yourself committed to takeoff. That said, if you experience an engine failure immediately after takeoff, you'd still have quite a bit of runway to aerobrake until below 102 knots maximum braking speed. If you abort above maximum braking speed, select idle but do not apply the brakes until at or below max braking speed if runway length permits. Once the aircraft is airborne, required climb performance is 200 feet per nautical mile unless otherwise charted. Taking off from runway 8 at Albuquerque, we see a minimum climb of 470 feet per nautical mile is required till reaching 7,600 feet. We'll use the climb gradient chart to determine our climb rate through 7,600 feet. Starting at 27 degrees Celsius on the left, trace right to 5,000 feet pressure altitude. At 5,000 feet pressure altitude, follow the contour line to 7,600 feet and then go straight down through 6,500 pounds gross weight to arrive at about 850 feet per nautical mile climb. To convert feet per nautical mile to feet per minute as you'd read on a VSI, refer to the rate of climb and descent chart found on the back cover of an approach plate book or in the Legends document in ForeFlight. As seen here, a 140 knot ground speed climb at 850 feet per nautical mile equates to approximately 2,000 feet per minute. Moving on to landing distance, let's look at how to figure out your heavyweight, no-flap landing distance. This is the worst case scenario runway length needed to land in the event immediately after takeoff you need to land but were unable to put the flaps down. This chart is ran just like the takeoff distance chart. It's worth noting the charted landing distance is based on being idle power at 50 feet AGL, touching down at 104 knots indicated, and using maximum braking technique 2 seconds after touchdown. As seen here, the no-flap max gross weight landing distance at Albuquerque is approximately 3,300 feet. This distance would increase if temperature increases, the runway sloped down, you land with a tailwind, the runway is wet or icy, or if you had to cross the threshold higher than 0 feet AGL. Conversely, landing distance decreases if flaps takeoff or landing are used, if temperature decreases, the aircraft lands with less than maximum usable fuel, or the runway slopes up. The last thing this lesson will cover is en route cruise. This topic was saved for last because it is a lengthy discussion. When it comes to en route cruise planning, there are 3 basic methods you can choose. PCL full forward, which gets you to your destination fastest but burns the most fuel in the process, max range, which will get you the furthest distance, or long range cruise, which equates to 99% of maximum range but yields a significant time savings. If you park the PCL in max for the cruise portion of the flight, the distance you can fly is greatly decreased. A much better option, especially if trying to fly further than about 300 nautical miles, is to either fly max range, as indicated on the AOA gauge, or long range cruise. ForeFlight is the most common planning tool used in T-6 flight training. ForeFlight uses long-range cruise performance data to provide fuel burn, true airspeed, and indicated airspeed at a given altitude with current winds and temperatures aloft. This performance data is derived from the long-range cruise charts in the abbreviated checklist and -1. These charts are pretty easy to use as long as you know the winds and temperatures aloft. Other than ForeFlight, you can get this information from Aviation Weather Center as seen here. For example, winds above Albuquerque at 12,000 feet are 270 at 7 knots, and the temperature is 12 degrees Celsius. Looking at the long-range cruise charts for 15,000 feet, clean configuration, no wind, and an average gross weight of 6,000 pounds, if the outside air temperature is 5 degrees, a fuel flow of 413 pounds per hour should give you 192 knots indicated, 254 true, and yield 99% total range that max range would give you. 3 side notes to add to this. First, the fuel flow only indicates in increments of 5, so either set 410 or 415 on the fuel flow. Second, the T-6 only shows indicated outside air temperature, not outside air temperature, so you'll need to refer to the conversion chart on page P8 of the abbreviated checklist. Final note, true airspeed is not displayed in the T-6 without some pilot input. To figure out true airspeed, you have to input some data into CALC page 2 on the GPS. Seen here, start with inputting your calibrated airspeed. Refer to page P3 of the abbreviated checklist to convert indicated to calibrated. At cruise airspeed, calibrated is 3 to 4 knots more than indicated. Next, input your altitude, altimeter setting, the outside air temperature, not IOAT, and then true airspeed will be displayed on the bottom line. When winds are calm, ground speed is the same as true airspeed. The last thing we'll do in this video is compare long range, max range, and max torque cruise performance. As mentioned, long range cruise is 99% range distance of max range, but with a significant time savings compared to flying max range airspeed. To put this to the test, a T-6 was flown in a MOA in order to compare long range, max range, and max PCL performance. In this test, the aircraft is flown at 15,000 feet with about 700 pounds of fuel, which puts the aircraft at about 6,000 pounds gross weight. On this day, the indicated outside air temperature was about 10 degrees Celsius, so long-range expected performance is based on -5 OAT. This chart is based on 0 wind. In the MOA, a heading was flown directly perpendicular to the wind to make true airspeed match ground speed as close as possible. First, we'll look at max torque cruise. As you can see here, the fuel flow is 505 pounds per hour, resulting in a true airspeed of 291 knots. At long-range cruise of 405 pounds per hour, the true airspeed is 257 knots. Max range, flying the triangle, is 300 pounds per hour and 195 knots true. Let's say you want to see how far you can go with 400 pounds of fuel before descending and landing with 200 pounds remaining. Based on true airspeed and fuel flow, according to the fuel flow conversion chart in the -1, at max torque you should be able to go 0.575 nautical miles per pound of fuel, 0.625 miles at long range, and 0.675 at max range. Assuming calm winds the entire time, constant ground speed, and fuel flow, that comes to 230 miles at max torque, 254 miles at long-range cruise, and 260 miles flying at max range. Using these numbers, long-range cruise gets you approximately 98% of the distance that max range could. Using max torque, this gets you 89% the distance that max range does. In terms of time, you can fly at max torque for 48 minutes before reaching 300 pounds of fuel remaining. At long range, the time en route is 59 minutes, and at max range, an hour and 20 minutes. In this example, long-range cruise costs you 6 miles of distance that you could travel with 400 pounds of fuel, but saves 21 minutes of time en route. That completes this lesson on T6 Told.